Lesson 10.6 is going to go back to the idea about exponential growth and decay. Now that we can solve for exponents using our logs, natural log and common log philosophy or theorems, we can go ahead and solve more complicated problems. For example, in carbon dating, we can find out the time of the problem, where before we would have to know that. So, certain assets like homes can appreciate exponential growth. You gain value for your home or increase in value over time. Others like cars depreciate, exponential decay, or decrease in value with time. Obviously, as soon as you drive a brand new car off the lot, you lose value. So we have some basic formulas. And these are formulas you should put on your cheat sheet, and they kind of are in two classes. So our exponential decay formulas can either take the form y equals a times 1 minus r to the t power, where r is the percent of decrease as a decimal, a is always your initial amount, t is always your time. For scientists, they prefer to use this model. It's also going to model the same equation. We just look at it a little bit different. Scientists like y equals a e to the negative kt. A is still your initial amount. E is that natural number. K is the constant for different substances. So K equals a constant. So it changes. So for example, carbon-14 is shown here as 0.00012. That information, you will either solve for it or be given it. Now, if you are looking at exponential growth, here are the two models that we're going to look at. Y equals a times 1 plus r to the t, where r is the percent of increase as a decimal. T is still your time. A is your amount that you start with, initial amount. Y is what's left or what's gained after that amount of time. Your scientific model is going to look really similar. Notice here that K is positive. It's growing, versus in the decay it's negative, which means we're losing. So you need to grab the right formula. If you're talking about a science model, you want to grab the one with E. If we're talking about other things, go ahead and grab the one that does not have E. So what does this look like? My favorite example. A cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for 90% of this caffeine to be eliminated from a person's body? Now notice that's because we're not putting any more in, so that kind of messes with our model. So 130 is our initial amount. That is what we are starting with. It's eliminated from the body. So this is a decay model. We are going down at a rate of 11% per hour. So R is 0.11, 11% as a decimal. How long? Time is what we don't know, okay? But 90% to be eliminated, well, Y is what's left in our equation. And so Y is going to be our 10%. Okay? So in this case, if we're starting with A is 130, 10% of 130 is 13. So if we put 130 milligrams in, how long will it take for only 13 milligrams to be left in your body? 90% gone, 10% left. So we're going to go ahead and use y equals a times 1 minus r to the t. This isn't a carbon dating, scientific decay, growth kind of model. This is pretty straightforward. So we're going to substitute. So if y is 13, I'm going to put 13 is equal to a is 130, 1 minus 0.11, and t is what we are solving for. So when I go ahead and simplify this a little bit, I end up with 1/10 is equal to 0.89 t. In order to get that exponent, that t, out of the exponent position, I'm going to go ahead and, since I'm not dealing with the natural number e, I'm going to take the log of both sides. Exponent rule says that that t is going to come down front, so I have the log of 1/10 is equal to t log of 0.89. Get t by itself by dividing by the log of 0.89, so I have the log of 0.1 divided by the log of 0.89 is t, and when you go to your calculator, you find out that t is 19.8, or approximately 20 hours for 90% of that caffeine from 1 cup of coffee to be gone from your body. That is why you don't drink coffee after 6 o'clock at night. The same would be true for soda. Sugar would have a similar sort of decay model. Medications would have a decay model like this. How long before enough of it is out of your system, in the case of medication, that we can give you more. So that's where these kinds of formulas come in handy. When we're talking science, in this case we're talking about a half-life of something, we are going to go ahead to our y equals a e to the negative kt. Half-life means decay. Things are going down. It is being cut in half over time. So what do we know? This is a formula we're going to use. So the half-life of sodium-22 is 2.6 years. What is the value of K? That's what we don't know for sodium-22. So we need Y, we need an A, and we need time if we're going to solve for K. K is what we don't know. Now, an easy way to look at this is if I start with 1 milligram. It doesn't really matter the amount I start with. I could start with 20, I could start with 100, but let's make my math easy. Let's start with 1 unit. So the half-life means that after 2.6 years, there is going to be half of whatever I start with left. So I can go ahead, I could make my numbers 150, 20, and 10. It's all going to work out the same, but why not keep it simple? So when I put this into my formula, I have that 1/2 is equal to 1 times e to the negative k times 2.6. So if I don't have to divide both sides by 1, because 1 times anything is anything. I am dealing with e. So to undo e, I have to take the natural log of both sides. And I can reorder that variable just to make life a little easier. The natural log of e is going to cancel, so I have the natural log of 1/2 is equal to negative 2.6k. If I divide both sides by negative 2.6, the natural log of 1/2 divided by negative 2.6 is k. When you go to your calculator, you find out that k is a constant value of 0.2667. So whenever you're dealing with sodium-22, the constant decay value is 0.2667. So a paleontologist is examining the bones of a woolly mammoth and estimates that they contain only 3% as much carbon-14 as they would have contained when the animal was alive. How long ago did the mammoth die? Well, we're still doing a science model, and we're doing decay. So we are going to go to our y is equal to a e to the negative k model. So we are going to need a value for y, a value for a a value for k, and a value for t. Those are our variables. We need 3 out of the 4 of those. So how long ago did it die? Time is what we don't know. Now we're talking about carbon-14, and on the very first page in the notes, I tell you that carbon-14, the K value, is 0.00012. That's a given. That is not something you need to know. And now I need to figure out this whole A and what is left. It contains 3% as much. So my Y, if I start again with all, one whole unit, 3% of much is there's 3% left, and as a decimal, 0.03. Now it becomes a plug and chug problem. So I have 0.03 is equal to 1e to the negative 0.12312 t. And our process is going to be basically the same as it was before. I'm going to take the ln of both sides, the variable, the exponent in the variable is going to come down front, and this ln of e is going to cancel, and so I will be left with this. If I divide both sides by that constant k, I will get the time, and as you would expect when you divide by a little decimal like that, as I would expect in the context of the problem, that woolly mammoth died over 29,000 years ago. And so that is an estimate of how long ago that critter died. So one more example in this section. The population of a city of 1 million is increasing, so now we're talking about a growth model, at a rate of 3% per year, so plus 3%. We're going to get bigger. If the population continues to grow at this rate, in how many years will the population have doubled? So since we're not talking science, we can use our y is equal to a1 plus r over t. So what are we looking for? We have y, we have a, we have r, and we have t. Well, since our question's saying how many years, t is what we don't know. R is 3%, which as a decimal is that. Now, the population is 1 million. I'm not going to put all of the zeros in, so I'm just going to put 1 for 1 million, and when it doubles, it will be 2 million. Now I know that I've truncated those numbers when I'm doing my calculations, and as long as I'm comparing 1 million to million, I'm good. Substitute. 2 is equal to 1 times 1 plus 0.03 to what I don't know. Since I am dealing with a straight exponent problem, I can go ahead and just take the common log of both sides. Exponent rule goes into effect. That variable is going to come down as a coefficient. Divide both sides by the log of 1.03. Is the time. Now if I get a negative number here, I know that I did it wrong. So t comes out to be about 23.4. So in about 23 to 24 years, the population will double if it continues at that same rate of growth, which there's lots of other environmental factors that affect that, but for the sake of the model, that's what happens. That is the end of the 10-6 lesson.